Have you ever seen the massive LED sphere in Las Vegas? The one that lights up the sky with moving images and animations? Imagine building something like that in your own workshop. A rotating LED globe that creates stunning 3D visuals in mid-air using just light and motion. In this video, I'm going to show you exactly how I built a persistence of vision spherical display from scratch. A do-it-yourself project that combines electronics, mechanics, and software into one mesmerizing device. It's the most advanced persistence of vision display I have made so far, and it's inspired directly by the Las Vegas sphere. At the heart of this build is a ring of 64 RGB LEDs spinning at high speed to create a 170mm wide globe. Through clever interlacing, I've pushed the resolution all the way to 128 by 256 pixels with 512 color variations, enough to play animated GIFs, short video loops, or even static images, all from a tiny SD card. What makes this project really special? First, it's designed to be simple and cost-effective, with as few parts as possible. Second, the entire display is wirelessly powered, so that there are no slip rings or tangled cables. And all the image control is handled by a powerful RP2040 microcontroller using its programmable I/O feature for high-speed LED multiplexing. There's even an optional ESP add-on that creates a full web interface so you can control the globe from your phone or laptop. In the next 30 minutes, I'll walk you through the entire process, from the user interface to video conversion, mechanical design, and software details. Everything, including PCB layouts, code, and 3D print files, is available on GitHub, so you can build one yourself, or even take it further. So let's dive in. Let's start by taking a look at how to control the display using a smartphone or a computer. The web-based user interface can be accessed from any standard web browser. On the home screen, you'll see a window showing the contents of the SD card. Image files have the extension RS64, and I've just selected such a file, and as soon as we do, the display immediately starts playing the contents. We can also select a playlist which defines which content to show, how long each item should be displayed, and whether to overlay a clock on the image. The device uses Wi-Fi to connect with the internet. There's a screen for configuring the Wi-Fi credentials. The information is stored in the flash memory of the device. There's also a feature for setting the time zone. You can simply select your desired zone from a list, and the display will instantly update the shown time accordingly. So let's go back to the home screen and select the playlist manager. At the top of the screen, you will once again see the list of files on the SD card. From there, you can select and open a playlist. However, I'd like to quickly show you on how to create a new playlist. Click on the corresponding button and enter a playlist name. The playlist will open in the lower part of the screen. As it is a new list, it will be empty at first. We now can select image files from the SD card and add them to the list. In this demo, we select the file with the wobbling liquid and the other file with the spinning globe. Finally, we check the box next to the file name, which signals that we would like to overlay the clock. And finally, we save our new playlist to the SD card. Now we can return to the home screen. I will search for the just generated new playlist and select it. The liquid with the superimposed clock shows up, and after a while, this spinning globe. For generating display content, ChatGPT turned out to be extremely useful. It can help with computations or generation of image files, including animated GIF images. An alternative is to download free video or image content. I would like to demo how to download a video from Pixabay and how to convert it into an RS64 file. So I select a video file, open it, and then click Download. I choose a resolution with more than 1000 pixels horizontally. The next step is to convert this file into the RS64 format. For doing so, I have developed a little tool that runs on my Mac computer. Just drag and drop the file, set parameters, and start the conversion. I should mention that this little tool is also open source and it can easily be ported to run on Windows as well. Once the conversion is complete, the RS64 file will show up. The only step left is to copy this file onto the SD card of the display. So this is how the video looks on the rotating sphere. Now that we know what the display is capable of, it's time to take a closer look at how it's built and how it works. This might be a good moment to explain why I'm using the black shell in this setup. Without these outer parts, the globe would be mostly transparent. Ambient light would reduce the contrast and interfere with the visual effect. That's why I decided to go with this design. So, here you can see the device without its outer shell. Now the functional structure of the rotating LED sphere becomes visible. Let's start by taking a closer look at the base, which houses the motor and the power supply. The motor is mounted vertically at the center and is directly connected to the top part of the device, the section with the LEDs. The power supply is built into a horizontally positioned circuit board. It serves two purposes: powering the motor and wirelessly transmitting energy to the rotating LED board. For this, a so-called Royer converter is used. It generates an alternating electromagnetic field. The lower circuit board contains a transmitter coil, while the upper one has a receiver coil. This setup allows a fairly efficient transfer of electrical power to the display without using slip rings. To render a stable and spatially consistent image, the LED board needs a reference pulse to indicate when a specific rotation angle has been reached. This signal is generated using a Hall sensor. The sensor is mounted on the rotating part and detects a magnet fixed to the static structure of the device. The 64 LEDs are mounted around the outer edge of the LED board. This means they emit light within the image plane to the left, to the right, or upward. That's also why I didn't use surface-mounted LEDs. SMD components would have emitted light perpendicular to the image plane, which wouldn't work for this design. On the right-hand side, you can see the RP2040 microcontroller, along with a 24-bit shift register. This register can control 8 LEDs at once. So the microcontroller drives 8 groups of 8 LEDs each, one after another in rapid succession. On the left side, you'll find the SD card that holds the image data. In the center, there is the ESP01S microcontroller. it can be plugged into a socket and is used for remotely controlling the device. In the next part of the video, I'll walk you through the assembly process of the display. I'll also share a few important tips that should make it much easier for you to build one yourself. So let's look at this image. It shows the main mechanical components. All components were 3D printed. And in this slide, you can see the electronic circuit boards. There's the power supply unit located at the base of the device, the receiver coil, along with a few components for voltage regulation, and finally the LED board with its microcontroller. The small additional board is only there to provide mechanical stability to the overall structure. On the backside of both supply boards, the coils are integrated directly as printed circuits. This design makes the setup not only reliable, but also easy to replicate. All PCBs were manufactured by JLC PCB. I ordered not only the bare boards, but also used their SMD soldering and assembly service. All the manufacturing files are available in my GitHub repository. Ordering custom boards is actually easier than you might think. The first step in the assembly is to mount the support plate onto the motor shaft. Since the hole in the plate is a very tight fit, I used a vise to press it onto the shaft. The correct distance between the plate and the motor can be measured using a caliper. The base of the device is assembled in 4 simple steps. I use embedded nuts in the 3D printed parts, which makes it easy to screw the circuit board and the housing components together. The LEDs are probably the most important components of the display. I'm using a 4.8 mm straw head RGB LED, which offers very high brightness. I'm ordering these LEDs online from led1.de. To solder the LEDs properly onto the PCB, the connection wires need to be bent at a 90-degree angle in the correct position. To make this bending process both precise and easy, I designed a custom bending tool and 3D printed it. The LED is placed into a slot in the tool and a lever is used to bend the wires exactly at the right point. Let's have a look how that works. Keep also in mind that the orientation is mirrored between the left and the right side of the board. This is due to the interlacing pattern. The LEDs need to be aligned identically when the board rotates 180 degrees. So now we can have a look at the bending result. And once the LED is properly bent, it can be soldered into place with ease. Soldering the LEDs requires a bit of experience, especially since the pitch is very small. Using a magnifying glass can be very helpful for inspecting the solder joints. This image shows the plastic parts of the rotor. They are assembled with just a few simple steps using screws. Now comes a very critical step, aligning the rotor relative to the axis of rotation. I have to admit I initially underestimated the importance of this part. Precise work here is essential, both to ensure smooth operation without imbalance and to accurately align the LEDs for the interlacing pattern. The photo shows the mounting plate on the motor shaft. This plate is extended with an additional disc into which 4 M2 nuts are inserted. The holes marked with the blue lines are used for the mounting screws, while the nuts marked with the red lines are used for fine adjustment. Please compare the left and the right photo. The goal of the alignment is to bring the symmetry axis of the LED board into perfect alignment with the motor's axis of rotation. This is done in two steps. First, the angle alpha is adjusted to 0, followed by the adjustment of angle beta. Here you can once again see the four M2 nuts that hold the adjustment screws. When you turn one of these screws, the nuts move up or down, shifting the entire assembly accordingly. To mount the LED unit, you first insert the two mounting screws. Then you carefully screw in the four adjustment screws. Using a pair of tweezers can be very helpful during this step. As you can see, all the screws are now in place. The next step is to adjust the alpha angle. To do this, a pointer is placed above the display. I use a screwdriver held in position with a tripod. By rotating the display 180 degrees, you can see the misalignment. The misalignment is then corrected using the adjustment screws. To do so, you first loosen the corresponding mounting screw and then fine-tune the position using the adjustment screws. As you can see, it now looks a little bit better, but you need to repeat this process until the LED board is properly aligned. The final step is adjusting the beta angle. Here as well, a pointer is mounted in front of the display using a stand. By comparing the LED board's position at 0 degrees and at 180 degrees, you can check if the alignment is correct. Keep in mind that due to the interlacing, there is a shift of half an LED width. So at 0 degrees, the pointer should hit the center of a specific LED, while at 180 degrees, it should point exactly between the two LEDs. Now we are almost done with the assembly. The only remaining step is to attach the plastic housing parts. Most of the components can be 3D printed without any support structures. However, the two dome halves do require proper support during printing. In the image at the top left, you can see how I configured the support structures for this purpose. I have already mentioned the shift in LED positioning between the left and right sides of the LED board. This image helps to illustrate that arrangement once more. You can see in the close-up the horizontal lines on the left side fall between the LEDs, while on the right side they hit exactly the center of each LED. This concludes the discussion of the mechanical setup of the device. In the next part of the video, we'll take a closer look at the electronic circuit. I used KiCad to design the PCBs. Let's start with the LED board. To make the schematic easier to read, it is spread across 3 pages. The first page shows the microcontroller along with some peripheral components. The RP2040 circuit closely follows the manufacturer's recommendations, which are well documented in the official RP2040 hardware design guide. The GPIOs are divided into 3 functional groups. GPIO 0 to GPIO 11 are used to control the LEDs. GPIO 12 and GPIO 13 form the I2C interface to the ESP01S, and GPIO 15 to GPIO 20 are used for the SD card interface. For programming the controller, a USB-C port is included. The data lines are protected against electrostatic discharge using a diode array. Unlike most Arduino-based projects, the SD card is not accessed via SPI. Instead, the 4-bit SDIO protocol is used. Bill Kryman, the author of the SDFAT library, has implemented the SDIO support for the RP2040 microcontroller. The SDIO interface allows for significantly higher data transfer rates, which is really an advantage for this project, since the image data is read from the SD card in real time and displayed immediately. The ESP01S microcontroller has only 2 GPIO pins. However, that's sufficient to connect it to the RP2040 via I2C. The second page of the schematic shows the 64 RGB LEDs arranged in an 8 by 8 matrix. Each RGB LED contains 3 individual LEDs, red, green, and blue. The anodes of the internal LEDs are connected together within each RGB package, and the anodes of each column are also tied together. To activate a column, its anodes need to be connected to +5 volts. This is done using 8 p-channel MOSFETs. The cathodes of the LEDs are grouped row by row. That brings us to the final page of the schematic, which shows the logic used to drive the LEDs. Let's start with the column control. This is handled by a 74 HCT138 decoder. The HCT logic family can be powered with +5 volts while still accepting +3.3 volt logic levels at its inputs. This is essential in our case. The RP2040 provides 3.3 volt signals on its GPIOs, but the P-channel MOSFETs require control voltages of either +5 volts or 0 volts to switch correctly. So the HCT chip acts as an ideal level shifter for this application. The decoder has 3 input bits and 8 outputs. These outputs are used to switch the columns of the LED matrix. They are connected directly to the gates of the MOSFETs. The binary value at the decoder's input selects one output line to go low, while all others stay high. This ensures that only one column is active at any given moment, protecting the circuit from overload. The LED driver receives data via a fast 24 MHz SPI interface. The driver current for each color channel can be set individually using 3 resistors. Since the LEDs operate in pulsed mode, on only briefly and then off for most of the cycle, the forward current can be safely overdriven. In this setup, the current is set to 75 milliamps, which is well within the limits specified in the data sheets for both the LEDs and the driver. This is the layout of the LED board. Implementing the LED matrix results in a large number of control lines which are routed in circular patterns around the LEDs. The LED board is a 4-layer PCB. The 2 inner layers are used as continuous grounding planes. This design choice was made because the LEDs are driven by short, high-current pulses with steep signal edges. Under these conditions, the PCB behaves like a waveguide. That means you have to consider not only the forward path of the signals, but also their return path, which must run in parallel to the outgoing signal lines. If this is ignored, the edges of the signals will become distorted. Crosstalk between the signal lines will increase, and electromagnetic interference, EMI, can become a serious issue. To avoid these problems, the design includes dedicated grounding planes. In the zoomed-in section, you can see that each signal wire is paired with a nearby grounding wire. This is another important step to optimize return path and maintain signal integrity. The power supply PCB was taken directly from my earlier rotating color display project, so I won't go into detail about this circuit here. As mentioned earlier, the complex coil arrangement of the Royer converter used for wireless power transmission is implemented as a printed circuit. The components are positioned around the edge of the board to avoid interference from the strong alternating electromagnetic field generated by the coil. The PCB with the receiver coil has several slotted holes into which both the LED board and the support board are soldered. The components in the center of the board are responsible for rectifying and stabilizing the voltage supplied to the LED board. Let's briefly talk about how the display is able to produce different colors. The three color channels of the LEDs, red, green, and blue, can only be either on or off. But to create a wide range of colors, we need to display intermediate brightness levels. The way to achieve this is through pulse width modulation. The ratio between the on time and off time of an LED determines its perceived brightness. The image below illustrates this concept. First, the color depth is reduced. That means we limit the number of brightness levels that can be represented for each color. This display supports 8 brightness levels from 0 to 7. To display them, 7 subpixels are shown in rapid succession, where the LEDs are either turned on or off depending on the desired brightness. The image on the right shows a close-up of the display. At this resolution, you can clearly see the individual subpixels which blend into a smooth color when viewed from a distance. It's quite interesting to take a closer look at the timing of the LED multiplexer. The spherical display rotates at a frequency of 10 revolutions per second. This means one full rotation takes 100 milliseconds. During each rotation, 256 pixels are displayed. That results in a time of 390 microseconds per pixel. Each pixel is divided into 7 subpixels, so the time per subpixel is 55 microseconds. And within that short time, 8 LED groups, each consisting of 8 LEDs, have to be addressed. That gives us 7 microseconds per LED group. As you can see, the control of the LEDs has to happen extremely fast. For software development, I used Visual Studio Code with the Platform I/O extension. This development environment is highly professional and well suited even for larger projects. One of its major advantages is that the entire configuration of a development project, including all required libraries, is defined in a single configuration file. When you open the project folder, the corresponding setup is loaded automatically. That makes Platform I/O projects very easy to share and reuse. The software for the rotating LED sphere is organized into two separate platform I/O projects, one for the RP2040 and another for the ESP01S. This screen shows the project structure on the left-hand side. Key parts of the code include the LED control logic and the handling of the I2C interface. All data and functions are neatly encapsulated in clauses. The software for the ESP01S includes a lightweight web server and communication over I2C with the RP2040 microcontroller. The web interface is stored directly on the microcontroller in the form of HTML, CSS, and JavaScript files. So, this concludes the presentation of the rotating LED sphere. I hope this project inspires you to build your own version or even to contribute and improve it further. All development resources, including PCB files, source code, and 3D model files for mechanical parts, are available for download on GitHub. Please note the licensing terms. You are free to use all files for personal builds and non-commercial development as long as you credit the original source when publishing your work. Educational and teaching use is especially encouraged and very welcome.